Section 6.3, graphical solution of linear programming problems. Just want to highlight something here in the first theorem. Again, you should be looking at these notes. They are posted in the lessons section within Isidore. So theorem number one, if a linear programming problem has a solution, then it must occur at a vertex or corner point. All right, we talked about that a little bit in section 6.1. In fact, a lot of this section will be based on what we have already discussed in section 6.1. Theorem number two in section 6.3, just to go over a couple things here. If the solution region is bounded, then your objective function will both have a maximum and a minimum. And again, those will be occurring at your vertices or corner points. If it is unbounded, if your solution region is unbounded, then your objective function will only have a minimum and not a maximum because the graph keeps going on indefinitely in the positive direction. These are basically the guidelines that we need to be following to use what are called the method of corners. Okay, so first thing we need to do is graph the feasible set. And in order to do this, we're going to be looking at techniques we've already discussed in section 6.1. At that point, we'll find all the coordinates of our vertices or corner points. Then we will evaluate those, evaluate the objective function at each corner point. All right, whatever vertex spits out the largest value, that's going to be a maximum. And whatever vertex spits out the minimum most value, the smallest value, that's going to be the minimum. So we're going to be looking at 5 examples in this section. The first 2 deal with the type in which the feasible set S has already been given to us. And then all we have to do is determine the maximum and or minimum of this objective function. So what you would do if you're given this information is you would set up a table and you'd have your vertex column and then you'd have your objective function column. And what you would do is in the vertex column, you would enter in all the vertices or corners. All right, so you put in all the vertices or corner points there. And then we would do what? We would plug in each vertex into the objective function. So if we're looking at 2, 6 first, we would get what? Well, the x would become a 2. So 3 times 2 is what? 6. So 6 minus the y value, which is 6. 6 minus 6 is 0. Okay, and then we do the same thing with this point, 7, 9. Replace the x with the 7. So 3 times 7 is 21. And then 21 minus the y value, 9. 21 minus 9 would be what? That would be 12. And so on and so forth. So 3 times, next point would be 10, 1. 3 times 10 is 30. 30 minus the y value, 1. That would be 30 minus 1, or 29. And then 2, 2. We have 3 times 2, which is 6. 6 minus the corresponding y value, 2, would give us 6 minus 2, or 4. So all we have to do now is state which one is our minimum, which would be the smallest value, which is 0, and then state which one is the maximum, which is not 4, which is 29. This is why you do not smoke crack before you teach math. So this one is not correct. This is the maximum, and this is the minimum. Okay, let's go on to example number 2. Example number 2. So the difference between example number 2 and the one we just looked at, example number 1, was that example number 1, to look at it again, was bounded, right? And so because it's bounded, we're guaranteed to have a minimum and a maximum, okay? Well, in our second example, this is not bounded. This shaded region would go forever up and to the right in quadrant number 1. At least it appears that I would do so, okay? Again, there's no solid blue line here making this be a bounded region, all right? So it's, again, unbounded. Because that's the case, we will only have a minimum value. We will set this one up the exact same way we set up the previous one. We have our vertex column, and then we have our objective function column. So all we have to do is plug in the ordered pairs into our objective function and determine which one is our minimum, most value. So let's put in our vertices. Put in our vertices in our vertex column, and let's go to work. So if x is 0 here and y is 20, we would get what? We would get 60. If x is 3 and y is 10, we would get 36, I think. If x is 4, that's 8. If y is 6, that's 18. So what is that? 2 times 4 is 8. 8 plus 18, I think that's 26. Okay, and the final one, 9 times 2 times 9, 18. Plus 3 times 0, that's 0. So this is going to be, what? 18. So 18 is the smallest outcome here in our objective column. Therefore, this is the minimum. And we're finished there, again, because this is unbounded. You will not have a maximum. This is not the maximum because it's an unbounded feasible region.